So I thought I'll give you an update what is currently behind or in the focal planes of the big telescopes. And, or in other words, I'm trying to answer two questions you may or may not have. Namely, so why don't we look through telescopes anymore? And I learned about at least one reason today in Alex is talking, you're short-sighted, don't look through the telescope. And maybe why are the instruments that we're building for telescopes are so big? Okay, let's start here. So, okay. Of course, you know that was Albert Einstein looking through the Mount Wilson telescope, so he was visiting the Hubble occasionally and to see if there is some evidence that his theories are actually consistent with what can be observed in the universe. But we didn't do that anymore. Yeah? So it was certainly good for Albert Einstein to do that. But why don't we do that actually anymore? And there are a couple of good reasons. Who of you has a telescope at home? Okay, and I presume you look through it for good reasons. Who of the people with the telescope do astrophotography? I mean, connecting a camera. Okay, very good. That has some advantages, obviously. For one, you can show all your friends and colleagues what it looks like, right? Which is hard. They will probably never listen to you describing that. So, obviously, one of the disadvantages of doing it like Albert Einstein is there's always an observing bias. You see something, you describe it, someone else looks at the same thing, and would probably describe it in a different way. Now, there is also, well, the human brain, of course, constantly processes the images that it sees. Right? So if you, after your eye has been adopted to the night sky, there is no point in looking at some faint feature for an hour rather than just a minute. It's not that you would see more. I mean, you just go crazy. Now, on the other hand, so this is an image of the James Webb image of the Hubble Deep Field. And if you pick one of the faintest dots in there, you probably would expect to receive about 1 photon per year in your eye from that very faintest galaxy at that redshift. Now, if you use a bigger telescope, of course, you get more photons. But still, you need to integrate, have an exposure time that is very, very long. I mean, you can do that already with photographic plates, which usually are not very efficient. But in any case, well, the eye is well, processing images, that's about the integration time of the brain, right? About half a second or so. And that means that you get reset, and so you don't see fainter objects, and that's why it sets your limiting magnitude at around 6 or so. Now, of course, we also want to record the images, to allow for digital image processing. And how do we make color images anyway? So the eye sees, of course, colors, and that's because in your eye you have receptors that are sensitive to different wavelengths, and the brain connects them and makes a color image out of that. Your smartphone works in exactly the same way. Usually, so you have your CCD pixels here, or CMOS pixels, and then you have some filter mask on top of it, and so some pixels only see green, some see blue, some see red. But that's actually not how astronomers take pictures. Usually we use the full focal plane and take one picture, and then do that through different filters, and we combine the filters. Now that has some advantages because it's more efficient, it's easier, it's also complete, right? You would feed, I mean, if a red photon hits here in the blue filter, it's just lost. I mean, it doesn't work for normal life, right? If you take a family photo and you say, well, don't move, I need to take the blue filter now, and then the green one. But for pictures like that from the sun, so these are 3 different pictures, and if you start animation, you can see when they combine, then you get a really, what looks like a real color image. Of course it's not, but that gives you then a real, well, an impressive color image in this case of the sun. Now, of course we want to also look outside the visible range. We just don't want to look at what we see, like in this case, at visible wavelengths from red to blue. We want to go to X-ray, and of course we need instruments to do that, right? Besides Superman, there are not many people who can actually looking at the X-ray, and then all the way out to the radio. And at every different wavelengths, you see something, different physical process happening. And then we also need images because the information that we can record in principle is huge. And just for reference, the information stored in the Bible corresponds to about 20 megabytes. That's the camera of the LSST, or now Rubin Observatory. And the data rate per night is about 20 terabytes, so that's 1 million times more than the information that's stored in the Bible. And actually, the human brain is quite efficient in terms of storage density. So the human brain stores about 2,500 terabytes. But so if you would drop everything else your brain needs to do and just use it for astronomical data storage, it would still overflow after about 100 days of observations with the survey telescope. So there is a good reason to use these big instruments, and we also can use them not only to take images. Astronomers want to do very different things. So we want to take wide field images for big surveys, see from, like the Rubin Observatory, where you can claim that you might be able to spot Earth-threatening comets or asteroids. But we also want to use high-resolution spectrographs to study the chemistry of the material in the universe, or to look at Doppler shifts of objects that are moving relative to us. We also want to build coronagraphs to block out the star, to possibly see planets nearby, and also high time resolution instruments, just to see the flickering of objects, or and of course there are many more. So all of that requires lots of instruments. And as I said, these instruments are very different from your cell phones. I just put a couple of examples here. This is the instrument called FEAR, so what you see here, and I use my fingers instead of the pointer. So this is the VLT, the Very Large Telescope, and if you see something reflecting here, that's the primary mirror of about 8 meters in diameter. And then the light actually, so here's the primary mirror, the secondary mirror is up there. This would be the 60 meters of Hawkins that Alex was referring to. But it's above here, and then it gets reflected back, and then there's a tertiary mirror, a third mirror, that redirects the light then horizontally to either that or that platform. On this platform here, we see, this is the whole instrument called SPHERE. That's for the detection of exoplanets. And so this is the size of the instrument. I'm not sure if there are any human beings on this picture. Well, anyway, you see these are the handrails, so this is about 1 meter. You can see these are 5 meters or so. So big instruments. This is MUSE. MUSE is a multi-object spectrograph, also ESO's Very Large Telescope. It looks great. If you have seen the Matrix movie, it reminds me a little bit of that. But these are cooling lines. Yeah? And so the instrument really is alive. You can hear it when you're in the room with it all the time, because you see all the cooling gases flowing in there. It has valves that are automatically controlled, because it has more than 20 identical channels just to get a larger field of view for the spectrograph. Now this is the gravity instrument for the VLTI, so where you combine the 4 VLT telescopes to form an interferometer. And so you have the beams come in here and beam come out from the beam combiner. This is how the gravity instrument looks like. This is X-shooter. You can also see this looks different because it's mounted now at the bottom of the telescope, right, in the Cassegrain focus. So this instrument moves as the telescope tilts, whereas the others are sitting permanently fixed on the platform. And of course that already limits the size. Nevertheless, you can see that it's a wide rig. And so you might ask, why are these instruments so big? Can't you make them smaller? And I've been trying to, think about a couple of reasons here. One of them is that the focal plane of the telescopes are huge, not in terms of field size. So this is the full moon, and I've just overplotted here what the VLT, the extremely large telescope, will see. That's more or less the maximum corrected field of view of the VLT. Yeah, well, you all did the test, so you know it's 39 meters in diameter. But typically, the larger the telescope, the smaller the field of view. In this case, it's about 1/3 of the diameter of the moon. But this field of view, physically, in the focal plane, where the telescope focuses, is about 1 meter in size. Yeah, 1 meter. Now, if you want to cover that whole focal plane, because you say, well, it's a big image, it has lots of information, you need a lot of detectors. And of course, you need a big instrument. I mean, we're not talking about the 5 centimeter lenses that Hubbles used. In order to get a 1 meter large image, you would need whatever gigantic lenses. Another reason is we want very often high resolution spectroscopy. And this is the UBIS instrument on the VLT. So and what you see here in the center, that's the UV grating. That's a high resolution grating to disperse the light. Just compare it to the size of the head of that person here. So you can imagine if the grating is already that size, and then the beam of the dispersed light is of course much larger in size. And so that all needs to fit somewhere in the telescope. Then of course, often we don't just want one spectrum, we want multiple spectra. Multiple spectra means this is an image of an instrument called hectospec at the multi-mirror telescope in Arizona. And what you see here, I don't actually know who the guy is, but what you see is that's the focal plane of the telescope. And what you can do then is to move fibers, optical fibers, at certain locations in the focal plane of the telescope. And then the light will be picked up by the fiber, and you send the light to a grating of the spectrograph, and then you get a spectrum. And so you just have to figure out where in the focal plane your favorite galaxy or star or whatever object is, and then you move the fiber there. This is actually done more robotic. It's very fun to see that work with all the robots. Sometimes they just mess up, and it's sort of a collision. It's a little bit like traffic in the rush hour. And then, this is about 1 meter there, also in size, and so obviously this has to be big. This is the moon's spectrograph, a very new instrument that will soon be see first light at the VLT in Chile. And what you see here are fiber bundles to different cameras, and look at the size of the camera. Right? Compare, this is not a real photo, but anyway, the proportions are about right. And over a field of view that of 500 square arcminutes, get lots of spectrum. Well, obviously you need a lot of information in the focal plane, or you have a lot of information, you need a lot of pixels, a lot of detectors. In this case, you've seen the picture before. This is, again, this camera at the Rubin, or a large synoptic survey telescope. What you see here in the focal plane, I haven't counted it, but according to Wikipedia, it's 189 detectors. Yeah, and each detector has 16 megapixels. So altogether, one readout, one image gives you 3.2 gigapixels. Yeah, and that's of course, that keeps many astronomers busy for a while. So, in fact, it's one of the problems, or challenges, or benefits, I don't know. You need a lot of astronomers to analyze that, or you need artificial intelligence to look through the flood of data to figure out what is interesting, what is relevant, and what is not. Well, and then many instruments need to be cooled. Yeah, so in this case here, why do we need to cool it? Well, on one hand, detectors often need cold temperatures. So our scientific CCDs are happy in terms of performance with something like minus 40 degrees Celsius. If we go to infrared detectors, usually we cool them to minus 200 degrees Celsius. And if we want submillimeter detectors, like in this case here, these are receivers in a cryostat for one of the ALMA telescopes. And in this case, of course, we talk about just a few degrees above absolute zero. And when you put those then in a big cryostat, of course, it makes a nightmare to align the optics because it's all enclosed in this gigantic cryostat. So I'm missing a scale here, but this is about 3 meters in height, I think. Yeah, just look at that structure. It takes forever to cool it down, like a week, and then warm it up. And then, cool it down, and you realize, oops, something. I get jealous of Hauchens, yeah, where just, oh, the lens doesn't fit, okay, I'll turn it a little bit. No, you have to wait a week until you warm it up, and then you fix it, and then, or maybe not. And then you cool it down and realize something has changed, and you can start over again. But in any case, it's very massive and very big. So, this is now, you've heard about this before, this is now a picture of the European Extremely Large Telescope. So you see in the background here, you see the ELT's 39-meter mirror. And maybe you can see here this honeycomb structure. Yeah, that's the darker spots you can see. So altogether, there are 798 segments of that mirror. What's not shown, of course, is the secondary mirror. In fact, the telescope has 5 mirrors, because it also includes adaptive optics to compensate for the atmospheric turbulence. And then after the 5th mirror, the light is redirected here horizontally to the Naismith platform. And on the Naismith platform, you can see that's high up above the ground of the observatory dome. And then on this platform, again, the optical axis is 6 meters above that. We're now, I mean, you can't believe we're now dealing with safety requirements that people don't fall down from the platform during the integration of the instruments. And then you see 3 instruments here. And one of the instruments, which is the instrument I'm involved in, working here, and I see 2 of my colleagues here, also here, Chad and Ivan, whom I work at Leiden Observatory to build this instrument here, which is called METIS. And yeah, we've made a movie, or ESO made a movie with our input. And I would like to show you the movie because it's, I think, a very nice illustration of what sits in the instrument and what it is. So, maybe you can. We have very sophisticated audio.
Set to start operating later this decade, the ELT will host a whole suite of high-tech instruments capable of matching its immense light-collecting abilities. Unique among them is METIS, the multi-tool instrument of the Extremely Large Telescope. METIS, or the Mid-Infrared ELT Imager and Spectrograph, will be operating in the mid-infrared. METIS is constructed with a 3-in-1 solution. First, it has its own adaptive optics sensor system, which works in tandem with the ELT's mirrors. It can measure turbulence in the Earth's atmosphere and correct for its blurring effects in real time. Then, the light is guided either to a high-contrast camera that will create sharper infrared images than ever before, or it is directed to the METIS spectrograph, which separates the light into its constituent colors. It will provide very high resolution and unsurpassed sensitivity and allow scientists to learn the chemical composition and motion of astronomical objects. METIS will weigh in at 18 tons, roughly the same as 3 well-padded elephants. Guiding the light through it requires a complex system with 243 optical surfaces, including over 55 precision polished mirrors. In the end, the light will have traveled 36 meters within the instrument. All of METIS science modules are encased in a vacuum chamber that can cool them down. This is essential so that the infrared light emitted by the instrument itself does not contaminate the signal.
Okay, so this was just a 2-minute summary. If you want to see the full movie, it's a very interesting movie. I strongly recommend it. Go to YouTube and just search for METIS and ELT. And then you should see the full 10-minute movie or something. And yeah, I think you've seen a lot of technical details. I don't want to take it too far. The beer is also waiting, the next beer. Let me therefore come to an end with a recent image of the James Webb Space Telescope. And I selected it for a couple of reasons. One is that this is a NIRCam, so the near-infrared imager of James Webb. took an image in 5 filters. So here you can see the 1.8 micrometers, 2 micrometers, 3.3, 4.4, 4.7, so at different wavelengths throughout the near-infrared range. And then the 5 images were combined. So of course this is an infrared image, so it's a false color image, so to speak. But of course it resembles what we would see with our eyes, with the shorter wavelengths being blue and the longer wavelengths being red. And so you see that image. And I think it's a beautiful image. It's like an artwork, right? You can print it on large scale and hang it at your living room wall next to your Vermeer or your Dali, and it wouldn't even stick out in any way, which is just works perfectly in, because it's so beautiful. I don't want to discuss the image, but at this point I also want to say another reason why I've selected it is because the image credit for the person who observed it goes to Klaus von Tobiton, who is one of our former PhD students in Leiden, and he's now a Space Telescope, and so he took the observations, and I think it's a beautiful image. It also shows what modern instruments can do, and now in this case, of course, on the James Webb Space Telescope, but I think we'll see many of these images from both ground and space-based telescopes in the future. Thank you.
Thanks for the great talk. Questions for Bernhard?
I'm wondering what's the key difference? Yeah.
Thank you. I'm wondering what's the key difference between the telescopes that are on the ground and those that we send to space, and why do we still need both of them? Like, what's the main difference in functionality? Because, like, from general person point of view, I believe that if you send something to space, it's kind of closer to the object, so the resolution might be better and stuff. So I'm wondering, why do we still build this huge on the ground?
Yeah, that's a very good question, and I think the distance doesn't make a difference, unless you observe Mars or so. Yeah, for a galaxy that's far, far away, yeah, it's like you from here you watch Paris, and then I would say, oh, I don't know where Paris is. I could see Paris much clearer than you because I'm closer. It makes no difference. The main reason is the atmosphere. Yeah, most people like the atmosphere. Astronomers have some problems. It's the turbulence and it's the absorption. So many of the, like here for instance, some of these wavelengths you would not see from the ground simply because the Earth would absorb, and because it also absorbs, it re-radiates the energy at different wavelengths, so the background is higher, and usually your sensitivity for a given aperture size is lower. So you get sharper images, especially when you do wide field imaging, where the turbulence is a problem. We have invented adaptive optics techniques that take out the turbulence of the atmosphere, but getting an adaptive optics corrected image over a wide field on the sky with uniform image quality is still an extreme challenge. So you can do adaptive optics correction in relatively small fields, but for imaging surveys, it's fine. So I showed you LSST before, the big survey telescope. Now they don't go to the ultimate resolution. They're happy with 1 arc-second seeing or so, because mostly they want to see whatever is there an asteroid hitting the Earth and destroying us all, or is it okay? And in this case, the resolution is fine. But if you want to really go to the extreme angular resolution or image sharpness that you have here, you should go to space. Now, the problem is, if you can get rid of the atmospheric turbulence, only then, right? Usually, if you don't get rid of the atmospheric turbulence, all of you who have a backyard telescope that's about whatever 30 centimeters in size or so, the image on the ELT wouldn't be any sharper than what you see. Yeah? Bigger telescope just means more photons if you're not able to correct the atmospheric turbulence. If you're able to correct the atmospheric turbulence, the image gets sharper the bigger the mirror. Yeah? So the 40-meter mirror then is 100 times sharper than the 40-centimeter mirror. And so this is what and there's the main advantage over, say, the James Webb Space Telescope. Because there is no way you launch a 39-meter telescope to space. The James Webb is 6.5 meters. You already had to wrap up and fold it, and everyone was happy that you could unfold it in the end. Yeah? But 39 meters, no way. And that gives you superior angular resolution, which is the key to finding, for instance, exoplanets. Because the exoplanets are so close to the star, if you don't have the angular resolution, no way to find it. And so the ELT will certainly find many more exoplanets than the James Webb Space Telescope by direct imaging, where you really just look for the exoplanet next to the star. The other thing is that we talked about the size of the instruments. High-resolution spectrographs just are big, they're massive, they need a lot of space. There is no way you launch that into space. So this is why it's very complementary and very expensive.
Other question?
I was just wondering, with the increasing number of satellites on orbit, have you guys ever kind of faced the issue that soon probably the Earth observation also will be difficult, even on such big telescopes? Will you have to build a software that also accounts for that when it processes the image?
It's a difficult question because whatever I say here is probably wrong in 5 years anyway. From the ELT, I don't think it's a problem. It's not a problem because it's a relatively small field of view and you observe for a long time and you filter images anyway. So if there are a couple of satellites passing through, we don't care. However, I would not generalize this because it's very different than if you do large surveys or so. I think at this point it's not a major issue. I mean, there are general challenges in many cases, right? If you, as much as we like green energies and you put up your windmills, the radio telescope in Drenthe will at some point, of course, have problems with electromagnetic interference. And so the same, of course, is also in space. The more you put there, the narrower the windows that were unchallenged in the times of Huygens are getting smaller and smaller. For good reasons often, but it doesn't help as well.
Maybe a bit of a critical question, but you did say that they're expensive to build these big telescopes. How would you say for, I don't know, a general person down the street, how would you argument that it is worth putting the money into building bigger and bigger instruments?
Yeah, they're expensive, yeah. Yeah, it's always difficult to compare the plain numbers, right? How shall I say, in the case of, I can give you some numbers here, right? The ELT is about 1.5 billion or milliard euros. An ELT instrument is in the order of about 100 million. James Webb was in excess, if you include operations, of 10 billion. Yeah? On the other hand, of course, this is scaled up for 30 years. You can also make a calculation where you divide the mission costs by all the people who work on it. And it turns out that these big projects are not necessarily more expensive than, say, one of our colleagues at physics or biology who has a lab space and just gets a little bit of money, but it also serves only him or her, yeah, and one or two students, whereas there are thousands, of course, in that. So within science, I think it's not extraordinarily large. Now, of course, the question always is in society, right? But you can, of course, also look for other costs. I mean, what did Volkswagen have to pay just as a fine for lying to people about the actual composition of their exhaust gases from the cars, right? That was you could build 30 ELTs for that money. Yeah.
Okay, if not, let's thank Bernhard again.